Alright, let's talk about chapters 27.1 to 27.4. We're going to talk about the wave aspect of light and how interference happens, Huygens Principle, and how that's related to diffraction, and then the double-slit and multiple-slit diffraction and the equations for that. Okay, so the previous couple chapters we treated light as rays and just imagine them entering lenses and being refracted and bending around. Well, if you get really close in where the wavelength of light starts to matter, now you can get some interference patterns based on the fact that light is a wave and not actually a ray. What that means is if I have a wave that's just a little bit out of phase, so they're not right on top of each other, you can get an overall wave that looks a little bit different. And what you can actually have sometimes is when a wave is perfectly out of phase, you end up adding them up and they get nothing. The idea with this is something called superposition, and it means this value and that value added together, if that's plus 2 and minus 2, when they add together you get 0, and that's true for every pair of points. So if two waves are perfectly out of phase, they're mirrors of each other, which means this one has positive values when this one has negative values. And the rule about waves is if you have two waves at the same point in space, they just add up, and the wave that you end up seeing is the combination of the two, and they just add together. So that's the wave aspect of light, is that you can get interference. Now this equation here says that the speed of light is constant, 3 times 10 to the 8th meters per second, but the frequency and the wavelength are directly proportional to each other. So in order to keep this equation where c is the same, if we increase the wavelength, we have to decrease the frequency in order to compensate for that change. So this is the relationship between wavelength, which is, for visible light, 300 to 700 nanometers. It's literally the distance from peak to peak. And the frequency is how long it would take for that to, for this peak to get back to that peak to get, and so on. And that's the frequency. Okay, in a medium, remember that the speed of light is related to the medium by the index of refraction, so it slows down in a medium. So the wavelength also changes inside of a medium, and it changes just like the speed of light, c over n. In this case, it's lambda over n. That just gives you the wavelength inside of a medium of some whatever index of refraction. Okay, so the Huygens principle with diffraction is the idea. It's not super important to understand this. I mean, it's kind of cool to think about, but it's a little bit weird. Basically, what the Huygens principle said, he was trying to explain why. Let me draw a flat surface. Why, when a light ray comes in, it bends towards the normal, and the normal is here. And so when we think about light rays, remember we're thinking about a single ray, but there's actually a bunch of rays of light, and they all come in and they all refract like this. And so we can treat something we call a wave front, where it's perpendicular to all of the rays that are coming in, and then as it approaches the surface here, you can see that it ends up bending. The wavefronts change. So why does this wavefront change? That's what Huygens was trying to figure out, and what he was saying was, okay, at every point there are little radiators, and as this wave approaches, this part of it hits this one, which then gets excited, and then time marches on, this one gets excited. When that one gets excited, this one's already started to spread out. Then this one gets excited, this one moves forward, this one moves forward, this one starts, and then this one gets excited, but this one moves forward, this one moves forward, this one moves forward, and then so on. And so you end up with this wave, a new wave front at a different angle forming. And so that's what his whole principle was, that the atoms, okay, and what you should take away from this is what actually happens. The reason inside a piece of glass, when light enters it, it hits these atoms, which re-emit light, which hits another atom, which re-emits light, which hits another atom, which re-emits light, which hits another atom, which re-emits light, and so on. And that's why that process takes time, and that's why light slows down in a medium. And Huygens was the first one to come up with an idea with that, and he said, okay, well, If we treat a single ray of light, the ray would be moving this way, all the rays would be coming this way. But the wavefront, if we treat it as made up of lots of little radiators that are constantly sending out their own signals, then as they expand out, so does the wavefront move forward. Okay, so that's the idea here. You got your old wavefront, your new wavefront, and it moves forward based on these radiators. Okay, and so this is just trying to explain the index of refraction, so it's a little bit confusing, and I understand that this isn't very well explained here, but that's the idea, and that's helpful because, and you need to understand that Huygens principle a little bit to try and understand when we talk about interference of light, because we imagine if there's a little doorway here, we treat these little radiators, and you end up with these little circles, and that explains how the sound ends up, or in this case the sound, they're trying to do an example of sound, but it's the same as audio, or sorry, light and sound do the same behavior because they're both wave-like. The light ends up diffracting around this corner, and so how do you explain that? So that's the Huygens principle, tries to explain this curvature at the edge, because the radiators are all radiating forward, but the ones at the edge, they don't have that ability, and so you end up just having the circles with nothing extending them, and so you end up with a diffraction pattern. Now the idea is that the pattern you see is dependent on the slit width, and you know, the ray comes out that way. So the Young's double-slit experiment, what this was sort of this final nail in the coffin that said light is a wave, because Isaac Newton he believed in what was called the corpuscular theory, that light was a particle, like a little ball of light, and it flew around and it hit stuff. And Huygens thought it was more of a wave, and Young came and did this experiment where he shined light onto two little slits, and what he saw was an interference pattern. And this is an interference pattern that you would only see when you're dealing with waves, and this was kind of a big deal. And here's this principle of superposition that says if two waves are in phase, notice in phase just means they're lined up, then the amplitude, which is x for each of these, is twice x, and you know, plus x, minus x, those are out of phase now. When this one's up, this one's down, so this plus x and that's minus x, they add together, excuse me, and the resultant wave then is 0. So this is maximally in phase, maximally out of phase, and when it's in phase you get twice the amplitude, when it's out of phase you get 0, and if they're at any other phase in between you get some combination of them. So this interference, this principle of superposition that only waves experience, if we imagine these waves traveling out away from these two little patterns, then they can interfere with each other, and then they end up creating this pattern, which is the crux of this chapter. We're trying to explain this pattern that we see, and it's based on the idea that the light is a wave. So with this chapter, what we're trying to teach you is how to think about light as a wave, and the principles and properties of waves, and how they work together to give this pattern that we see, and then some little bit of geometry to understand it. So what is this a picture of? It's a wall with two little slits cut into it, rays of light shining on there, and then the rays of light both spread out and they hit the wall, and where they hit the wall you see a pattern like this. And so during the in between the screen and the wall is this, and let's see, moving on. And so what we're trying to do is explain what, you know, how do you explain this pattern? How do you explain that? What are the calculations that go into it? Well, the calculations that go into it are the distance you are from the screen, the separation of the slits, the thickness of the slits, and that's pretty much it, and the wavelength of light itself. Okay, so what you're doing here is you're imagining a bunch of triangles, okay, and then when when this wave hits that screen or this wave hits that screen, when they hit here, hopefully you'll agree with me that those two lines are different lengths. If they're different lengths, then these green lines are going to be different. So what if this line started back here a little bit? Now they would be out of phase. And so by the time they reach up here at the top, they could be in such a distance that they're out of phase from each other. If they're out of phase from each other, then you get an interference pattern. If they're in phase, you get a bright interference pattern. If they're out of phase, you get a dark interference pattern, and somewhere in between. And so that's what this is a picture of, is the laser interfering with itself as it goes through those two slits and creating that pattern. So we're going to talk about the math necessary to do that. So this is the idea that if the path length from here to here is off by a wavelength or so, then you end up, see the wave is up and down here, then those two add together negatively, you get 0. In this case, up, and you get positive. Okay, so for constructive interference for a double slit, if you want to see where the bright lines are going to occur, so for example, there's like 1, 2, 3, 4, 5, a bunch of little bright lines there. If you want to know where those will occur, they occur when this little length here, because this length and that length are the same length, the only difference is that little bit, which turns out to be d sine theta. So you want d sine theta, which is the length, the extra path length, you want that to be a whole number of wavelengths off for constructive interference, but you want it to be a half of a wavelength off for destructive interference. So you could have a line there, you could have a line here, you could have a line here, a line there, a line here, a line there, and you'd have bright, dark, bright, dark, bright, dark, bright, dark, bright, dark, bright. And the case for that happens when this extra path length, because you imagine these waves going like that, that extra path length is off, so you're out of phase or in phase, and then somewhere in between for each of those. Okay, when m equals 0, you're right at the center. When m equals 1, you're at the first fringe. When m is 2, you're at the third. When m is 4, you're at the fourth. When m is 5, you're at the fifth, and so on. So you'll have 1, 2, 3, 4, 5 fringes, and that's what you're trying to predict with these equations. Okay, and so this is another way to draw it. You've got the distance to the screen, the angle up to the screen, y here, there's your triangle, the separation d between the two slits there, that gives you the pattern, the bright, dark fringe there. And so, here's an example. Suppose you're at, the slits are this far apart, the angle's up to there, the wavelength, what is the wavelength of the light? And so you just say, oh, the wavelength is d sine theta over m, and we're talking about the third bright line, so we're going to put m equals 3 in for, or 3 in for m, and you get this, you get 633 nanometers. Okay, and blah, blah, blah. Okay, so for multiple slit diffraction, you end up with, instead of 2 lines or something, you just put a bunch of them in there. That's called a diffraction grating or multiple slit diffraction. But a diffraction grating is used to produce some really cool images of stuff. Pretty sweet. Okay, so the difference between the double slit and the diffraction grating is you see there's a little bit difference in the brightness and the intensity of the different minima and maxima. Okay, so but you're basically doing the same thing. You have the same d sine theta equals m lambda for constructive interference, and d plus a half sine theta for, or d sine theta equals m plus a half for destructive interference. Same idea. Okay, so a diffraction grating is just the same type of thing as a double slit grating. Okay, and then so we'll talk about single slit diffraction in the next video, and I'm not quite sure why they do single slit afterwards. What you should pay attention to for single slit is that so if we look carefully at this pattern, you can see that there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? Look at all those fringes. So there's a lot of M's here. M is 0, M is 1, M is 2, M is 3. Okay, but if you look closely at this, you can see that there's a overall kind of bright, dark, really bright, dark, little bright pattern there, where that's really bright, 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 but there's a dark fringe, dark fringe, dark fringe. So that overall bright, dark is from the single slit part of the double slit. So you've got two double slits, two single slits working as a double slit. Those two working together give you this overall pattern. You'll have the overall pattern that you'd have in a normal just single slit, but then that fine pattern that you see, the multiple bright, dark, that is from the single slit. So a single slit diffraction pattern looks like that. A double slit diffraction pattern looks like that. Okay, it's just got more resolution in it, more flips in it. So pay attention to that when we're talking about the single slit here, the next video. Okay, bye.